Hello dear viewers, I hope now you have seen my earlier videos on Kirchhoff's law, superposition theorem, Thevenin's theorem and Norton's theorem. The same problem was taken for illustration of the various theorems and laws and all that. I now feel that we should have some tutorial. We should solve some mixed type of problems so that we will have a good mastery on the solving of such problems. So one such problem I have taken. Now see, in those earlier videos, there was a problem taken in which there were three power sources, but all were the voltage sources. But now let us have some combination of voltage as well as current sources. So this is some problem that we deal first. Okay, now the problem statement is that find current in 4 ohm resistor. They have not mentioned whether you solve it using superposition theorem or with simple Kirchhoff's laws or Norton's theorem or Thevenin's theorem. So you are free to solve the problem with any of these methods. And we know that we can find out the current in this 4 ohm resistor. In this diagram, the 4 ohm resistor is placed here. So our job is to find current flowing in this 4 ohm resistor. Now let us solve this problem with all the methods one by one. Okay, suppose let us first we deal the problem with only simple Kirchhoff's laws. Okay. Now remember, before you start solving this problem, I will just give you one simple idea that will make your solution very simpler. You first identify the current sources in your given diagram or given circuit. Now see here, in this circuit, there are two current sources. One is here, 2 ampere, sending current in this direction. One more is here, 6 ampere, sending current like this. And also, there are two other sources, those are the voltage sources. So it is some combination. Two voltage sources operating as well as two current sources in the same circuit. And our job is to find out current in this 4 ohm resistor. So the idea is like this. You first identify your current sources and just replace the current sources in a way, replace those branches in a way that I am going to tell you. Now see here, this current source as well as this resistor, they are in series, but they are finally connected across these two nodes. Now see, this is very important. You identify across which nodes that particular branch is connected. Now see here, these are the two nodes, and across these two nodes, this entire branch is there, which is having the current source. Now see, there is a simple meaning to that. The meaning is that when we say that there is a 2 ampere current source acting here, the simple meaning is that this source is sending a current of 2 ampere in this direction. That's all. So finally, this 2 ampere current is going to reach to this node. So at this node, 2 ampere current will be incoming. Whereas at this node, what will be the picture? Since this 2 ampere is moving like this, that means here 2 ampere is entering like this into the source. So simply it means this way, 2 ampere current reaching to this node or 2 ampere current leaving this node in this branch. Once you do that, then a simple thing, you just scratch this entire thing from your diagram. Just leave it open like this. Keep it hanging like this. Let it be in this manner. So that entire branch where the 2 ampere current source was placed, it only meant that that branch is sending the current of 2 ampere to this node, or that branch was taking a current of 2 ampere from this node. Okay, now we have seen for the first source. Secondly, there is one more current source that we have identified. It is here. Again the same thing. It means that now see this current source as well as this resistor. They are connected across these two nodes like this. Okay. Again, what is the meaning here? The meaning is here is that this 6 ampere source is sending a current of 6 ampere in this direction. So suppose we show it like this, 6 ampere. Also it means that a current of 6 ampere is taken from this node. That is the only meaning. So we have marked now. This entire branch will provide a current of 6 ampere at this node, or this entire branch will take a current of 6 ampere from this node. And once we do that, again we just remove the things and keep the points just hanging like this. So this is very important idea before you start with your final solution. Okay. So two sources were there and we have marked the currents like this. And now see, now you go to your procedures. Now you use Kirchhoff's laws, you use this circuit for superposition theorem, for Thevenin's theorem, Norton theorem, anything. Okay. Now suppose we solve the problem with Kirchhoff's laws. So whatever circuit was given, you can replace the circuit with such a circuit. What is the idea? Idea is that you identify the branches in which current sources are there and just omit the branches from the circuit, but while omitting, you just mention the supply of the current at a particular node or taking out of a current from a particular node. That we have done. Now see, suppose we solve with Kirchhoff's laws. Now how many loops are there? That is the first thing. You will find that this circuit has only one closed loop and that is only this one. Like this. You cannot consider this as a closed branch now. Also you cannot consider this as a closed branch. So just one single loop. Okay, so one current variable will be there. Okay, we now identify the loop like this. Okay, our loop is like this. From this point here, then here, down, left, and again to the original point. And now see how to distribute the currents. See 2 ampere, suppose we start from this end. 2 ampere is coming to this node. However, there will be two paths. Means we need to take one variable. And now earlier we have identified also that since there is only one loop or one mesh, we will need only one current variable. So suppose I assume here that the current supplied or say current flowing here is say I. No need to say I1, I2, I3 because only one variable we want. So we just mark some current, unknown current I here. Now see 2 ampere is coming to the node. I is also coming to this node. So what will go ahead in this direction? It will be I plus 2. Okay. Now this I plus 2 reaches here. Now let us study at this particular node. I plus 2 is coming from left, whereas 6 ampere is coming from down. That other battery was giving. So I plus 2 plus 6 will be I plus 8. That current will move ahead like this. So this current in this resistor will be I plus 8. Now see, I plus 8 reaches here. Out of that 2 ampere is moving out of the circuit. So I plus 8 minus 2. So current coming down here will be I plus 6. Now this I plus 6 will flow ahead. Here also it will be I plus 6. Now I plus 6 comes over here. Out of that 6 is going out from here. So I plus 6 minus 6 will be current I. And see here the current I matches to our current distribution. So this is the simple idea for solving the problems having mixed type of sources, voltage sources or current sources. Now see, this is the thing. So one loop which we have identified, one variable just we needed obviously, and so just write the loop equation. So I will say that loop equation. Remember we are solving with Kirchhoff's laws now. So this part is the solution with Kirchhoff's laws. So loop equation, let us start from this point. Now our closed loop will be only this one, okay? So from this to this, it will be minus 2 times I plus 2. So resistor is 2 ohm and current is I plus 2. So minus 2 times I plus 2. Now from this point onwards, current is I plus 8, resistance is 2. So minus 2 times I plus 8. So minus 2 times I plus 8. Now we have reached here. We come down. Now here from negative to positive plate we are jumping. So voltage rise. So it will be plus 8. Plus 8. Now we have come to this point. Then left. Now this resistor is 2 ohm. Current is I plus 6. Again a drop. Minus 2 times I plus 6. So minus 2 times I plus 6. Now we have reached up to this point. Then further left. Resistor is 4 ohm. Current is I. So minus 4 times I. So minus 4 times I. And then from this point again to the starting point. Again there is a battery. We are jumping from negative to positive plate. So a voltage rise of 4 volts. So plus 4. And now we have traversed the entire loop. So this all thing will be equal to 0. and just simplify the equation. It is only one variable, one equation. Let us solve it. So minus 2i minus 4 minus 2i minus 16 plus 8 minus 2i minus 12, then minus 4i plus 4 must be equal to 0. Okay. So we are just now simplifying the things. So minus 2i minus 4i, again minus 2, minus 6i, and minus 4i, minus 10i. So minus 10i, and then all constant terms. Minus 4 minus 16 is minus 20. Minus 20 plus 8 is minus 12. Minus 12 minus 12 minus 24. Minus 24 plus 4 minus 20. So minus 20 must be equal to 0. That gives you 10i equal to minus 20, and so I equal to minus 2 ampere. So as I is coming minus 2 ampere, maybe now the distribution or the direction of current would be opposite. Now see here, our job is to find out current in the 4 ohm resistor as per the problem. Now look at our diagram and see what current was flowing in our 4 ohm resistor. As per our current distribution, current I was flowing through 4 ohm resistor. And what value we have got for I? Minus 2 ampere. So magnitude we know 2 ampere. Minus sign indicates that the current must not be from this to this end, but it must be from this to left to right. Okay, in final circuit. So if you identify the points like anything, say A and B, then you will find that in our distribution it was from B to A and the value was I. We calculated value of I as minus 2. Since the answer is coming negative, that means the actual current must be from A to B. That is the only significance of the signs. Otherwise magnitude is 2 ampere. So what is our conclusion? Our conclusion is that current in, so finally we have to write like this. Current in 4 ohm resistor is equal to 2 ampere, and then in bracket we just mention the direction from A to B, because we got negative answer. This way the given circuit is simplified and we can solve it. Now let us see the solution of the same problem by using Thevenin's theorem. Okay, so let us use the steps now, those steps which we have studied in the lecture on the Thevenin's theorem. Okay, what is the first step? First step is you have to remove that resistance in which we want to find out the current. What is our problem? Our problem is to find the current in this 4 ohm resistor. See why this circuit I have taken again. Because once you convert the circuit into this particular fashion, because we have taken care of the current sources, whatever current they were supplying or they were taking from the concerned nodes, that we have already managed into our circuit. So again for Thevenin's theorem, we will take the same simplified circuit. So first step, the resistance in which we want to find out the current should be removed from the circuit and it should be denoted as RL. Okay, now we want to find out current in this 4 ohm resistor. So our first step would be just to remove this resistance from this circuit, and whatever open terminals we get, those points we will mark conveniently, say letter A and B. So these were the end points of that load resistor, and we have marked them say as A and B, and here in this corner we will write our load resistance is 4 ohm. So first step is over in the Thevenin's theorem. Now what is the second step in Thevenin's theorem? Second step is that whatever circuit now you get after removing the load resistor, you distribute the current and write the loop equations and find out various branch currents. Now see, for this current is fixed, for this current is fixed. For some other branches we don't know the current. So see here, now we have to distribute the current. 2 ampere is coming like this, but will anything flow in this? No, because now it is open here. So don't distribute current, any current here for this arm, because it is open here at this end. Okay, so entire 2 ampere will flow like this. So 2 ampere goes. Now this 2 ampere reaches here. Now 2 ampere from this side and 6 ampere from down. 6 plus 2 is 8 ampere here. Now 8 ampere reaches here. Out of that 2 ampere goes up out of the circuit. So 8 minus 2 is 6 ampere will come down like this. Now the same 6 ampere will come like this. And you will find that this entire 6 ampere is again leaving this particular node. That means our current distribution is over. Remember again, don't distribute any current here, because after removing the load resistor, this branch or this end remains just floating, open. Okay. And see here, all these figures will be matching here. So 2 ampere coming like this, no current from this section. So entire 2 ampere will move ahead. Here at this node 6 ampere is added. 2 plus 6 is 8. 8 will go ahead. Out of 8, 2 is again leaving the circuit, and so 6 will come down. This entire 6 will flow up to point B, and from point B there is a drain of 6 ampere. It is going out. So the things match like this. Okay. So we have distributed the currents. Of course, for this circuit, we did not require to assume any current variable, because the currents, our problem is solved. What we want finally is to distribute the current and find out various branch currents. That only we want in the second step. So that we have done. We know now all the branch currents. And further, now next or third step is to find VTH. How to find VTH? We have to assume a fictitious or imaginary voltage source across the open terminals. Okay. Suppose I assume it like this. Now again here you can show any polarity. I have shown positive connected to A, negative to B. You can show in reverse way also. So this is our VTH. So we are moving to the next step to find VTH in Thevenin's theorem. And VTH is some imaginary voltage source connected across the open terminals. Now see, after we connect imaginary source, you immediately get some closed loop here. So you are getting this closed loop because you are now connecting points A and B with some source. For the time being, it is there acting. Okay. So it is like this. So this loop you get, this entire loop. From this point here, then here, down, left, further left through VTH, and again to the point, same point. Now what is done next in the procedure of Thevenin's theorem? Consider any closed loop which will contain VTH. Now we have only one closed loop like this, and obviously, or of course it is now consisting the VTH, and write the loop equation. So let us write loop equation. Starting from this point, this to this, it will be minus 2 times 2 ampere. So minus 2 into 2. Because current is known now here. Then from this to this, resistance is 2 ohm, current is 8 ampere, but it is a drop. So minus 2 times 8. So minus 2 times 8. Then this to this, it will be jumping from negative to positive plate. So plus 8. So plus 8. Then this to this left, again a drop, resistance 2 ohm, current 6 ampere, minus 2 times 6. We have reached to point B, and now towards left, we come, or say we go along VTH now, towards left, we are jumping from negative plate to positive, so voltage rise, so plus VTH. So plus VTH. And then from A point to the starting point, this to this, again jumping from negative to positive plate, so lower to higher potential, so plus 4. So plus 4. Now we have traversed the entire loop. We will say all this equal to 0. Just simplify it. Minus 4, minus 16, plus 8, minus 12, plus VTH, plus 4 equal to 0. So this minus 4 plus 4 will go. So what is the total now? 16 and 12, minus 28 plus 8, so minus 20. So minus 20 plus VTH must be equal to 0. Hence, the value of VTH comes out to be 20 volt. Okay. And since we are getting plus value, that means whatever polarities we had shown earlier blindly, those polarities must be correct. That means point A must be at higher potential, B must be at lower potential. Means in actual practice, when 4 ohm resistance is connected or it is replaced, then the current would be flowing from A to B. That would be the answer, final answer. But now we are interested in value of VTH, and that we have calculated. So here I will write VTH is calculated as 20 volt. And now the next step in Thevenin's solution is to find the net equivalent resistance of the entire circuit across those two open points A and B. And we have to take only passive circuit for that. Okay. So what we have to do? Only take the passive circuit. So this VTH, we don't want all this now. We want just a passive circuit. So we just remove it. You will find that there are two batteries. Again, there nothing is mentioned about their internal resistances. So for getting a passive circuit, we must replace these two batteries, both these batteries, with the help of a simple short circuit. So the circuit will be like this. Point here, then this resistance is 2 ohm, then this resistor is 2 ohm, then this another source is also shorted, then point A here, point B somewhere here, this resistance of 2 ohm, that's all. Only this circuit we will get. Again, see clearly in the circuit. Point A here, this battery shorted, so it will be from this to this. Then this to this is 2 ohm, that we have shown here. Then again there is open here, so this to this is next 2 ohm resistor here. So we reach here. Then this to this source also to be shorted, so we come like this, short circuit. Then this to point B will be 2 ohm, and again nothing there. And you will find that in your equivalent circuit, very simple equivalent circuit we have got, across A and B, all these three resistances are coming in series. So 2 plus 2, 4, 4 plus 2 is 6 ohm. So what is the value of RTH? RTH is equal to 6 ohm. Okay. So that is the next step that we have done. So here I will write RTH as 6 ohm. So all the three values we have calculated now. Just next job is to draw the Thevenin's equivalent circuit. So it will be like this. So Thevenin's equivalent circuit will have VTH here, and its value is 20 volt. Then RTH in series, its value is 6 ohm, and then point A here, point B, and then we have to replace the load resistor. Load resistor is 4 ohm, so RL must be equal to 4 ohm. So this will be the Thevenin's equivalent circuit for the given circuit. And now very simple, if you denote some current in load resistor, suppose current I, then what will be the value of I? Value of I must be equal to VTH divided by RTH plus RL. Just substitute the values. VTH is 20, RTH is 6, and RL is 4. So 20 divided by 10, this is equal to 2 ampere. So we have got the same answer when we solve the problem using the steps of Thevenin's theorem. See, current I in load resistor comes out to be 2 ampere. Same answer we have got as we have obtained with by using only the Kirchhoff's laws. Okay, and direction, obviously direction, since we had connected plus positive of this VTH to A, means A is at higher potential, B is at lower potential. Obviously in the circuit the current will be flowing from A to B. Here you can just add it, that from A to B. So this will be the solution of the given problem using Thevenin's theorem. And now let us move to the solution of same problem by using the Norton's theorem. Now let us use the various steps of Norton's theorem. First step, the resistance in which we want to find out the current is to be removed from the circuit, and we have to mark the open terminals with some convenient letters AB, MN, XY, like that. So we have to remove this 4 ohm resistor because our job is to find out the current in this 4 ohm resistor. So first step in Norton's theorem, just remove it. So we have now removed the 4 ohm resistor. We have marked the terminals, say with letters A and B, and here we write the load resistor is 4 ohm. So first step is over in Norton's theorem. Now second step in Norton's theorem is that, what is the second step? For the time being or temporarily, we have to short the terminals A and B. Okay, so we will do that. So here we short the terminals for the time being. Okay. Now we have shorted the terminals. Now next thing is just to find out what would be the current in this shorted branch. So simple thing, just distribute the currents, use Kirchhoff's laws. Anyway, you calculate the current in this shorted branch. Now again let us see what is the current distribution. You will find that after shorting the branch, we get just one closed loop, and then we need one current variable. So 2 ampere is coming like this. Suppose we assume that current here is I. So 2 and I coming here. So current moving ahead will be I plus 2. Again at this point 6 ampere is adding. So I plus 2 plus 6. This current going ahead will be I plus 8. Then I plus 8, 2 ampere goes away. So current coming down here would be I plus 6. This I plus 6 will come down here. Here also it will be I plus 6. Now out I plus 6 will reach here. Out of that 6 is going out. So current I will be moving ahead. Okay. And you will find that this I matches here. Our current distribution is proper. So as per our current distribution, a current I is flowing through short circuited branch. So we are interested in finding out the value of this I. Okay. Now one loop is there. So let us choose the loop. Only one single loop. So this would be the direction. Start from this point. It will be minus 2 times I plus 2. So minus 2 times I plus 2. Then ahead it will be minus 2 times I plus 8. So we have reached here. Then coming down will be plus 8. Then towards left it will be minus 2 times I plus 6. Then here no component, so no voltage rise or drop. And then coming back to the original point, it will be plus 4. So plus 4 must be equal to 0. Let us simplify this equation. It will be minus 2I minus 4 minus 2I minus 16 plus 8 minus 2I minus 12 plus 4 equal to 0. So minus 2I is minus 4I. Again minus 2I is minus 6I. So minus 6I. And the constant terms, minus 4 minus 16 is minus 20. Minus 20 plus 8 is minus 12. Minus 12 and minus 12 minus 24. Minus 24 plus 4 is minus 20. So minus 20 must be equal to 0. That means 6I must be equal to minus 20. So I must be equal to minus 20 by 3. That means it will be minus 20 by 6. It will be minus 10 by 3 ampere. And now see, I is coming minus. That means the actual current must not be like this, but it should be opposite. So here also we get that the current, as per our distribution, it was from B to A, but we are getting minus answer. So actual current must be flowing from A to B. Here we will write, that means it is plus 10 by 3 from A to B. And remember, this is nothing but, because what is I? I is the current in shorted branch. That means in Norton's theorem, this value must be equal to the Norton's equivalent current value. So this is nothing but the value of IN. So value of IN is 10 by 3. Okay. So here we write second answer, that we got IN as 10 by 3 ampere. Okay. And now third step is to find the value of Rn, Norton's equivalent resistance. We will not waste a time into that, because earlier while solving with Thevenin's theorem, we have already calculated value of RTH. In Norton's theorem, Rn is same as the value of RTH as in Thevenin's theorem. Okay, so what was that value? That we will just consider here for the next solution or the final solution. So let us do the final solution here. We know that we had got the value of RTH as 6 ohm while we were solving with Thevenin's theorem. That means definitely, because same thing we have to do again, that means we know the answer that Rn must be equal to 6 ohm. Because we will not repeat the same procedure because we have solved the problem earlier. So all the three values we have got. Now just to draw the Norton's equivalent circuit. What is Norton's equivalent circuit? A current source like this, then a resistance parallel, then our open points A and B like this. What is this current source? It is nothing but IN. What value we have got for IN? We have got 10/3 ampere. So we will just write it here. Now why again we have taken arrow like this? Because we know that current was flowing from A to B in load resistor. Only this arrow will indicate that the current will be flowing from A to B. Now this value in Norton's theorem is Rn. That we have got as 6 ohm. And then we introduce the load resistance across the same 2 points A and B. RL is 4 ohm. And finally, if we assume that current in load resistor is some current I flowing from A to B, definitely I must be equal to, what is the formula for that? IN, total current, into bracket Rn divided by Rn plus Rl. Just substitute the values of all these parameters here. So IN is 10/3 into bracket numerator Rn is 6 divided by Rn plus Rl. So 6 plus 4. So we will get it as 10/3 into 6/10. So we will find that again 10 will be cancelled and 3 2s are 6. Again we get the same answer of 2 ampere. Okay. So finally we have calculated with Norton's theorem also the current in load resistor must be equal to 2 ampere. Okay. Here we again means we have cross-checked the answer of the same problem with three methods: Kirchhoff's laws also, Thevenin's theorem also, Norton's theorem also. For considering the same problem with superposition theorem, that also we will do. And there are certain, that is somewhat different because you know that in superposition theorem, we have to consider every source at a time. So in the procedure of superposition theorem, all those current sources which we had removed for this operation, those we have to consider individually. But that also we can do, and we will find that with superposition theorem also we get the same answer. Okay. Here we will make some remark on Norton's and Thevenin's equivalent circuit. We know the values. See now, Norton's circuit we have got. If we convert this particular source into equivalent voltage source, what will be the case? The equivalent voltage will be this current into this resistor, INRN. So 10/3 into 6 will be 20. That means the voltage source will be of 20 volt. And the same resistor of 6 ohm will be in series. So this should be actually the equivalent circuit to be obtained from, or as obtained from, the Thevenin's theorem. And you cross check, while we were solving the same problem with Thevenin's theorem, we have got the same circuit, this circuit, as the Thevenin's equivalent circuit. Okay, that's why it is said that Thevenin's theorem and Norton's theorem are complementary to each other. So in short, this is the way of solving the problems or the circuits having mixed type of sources, means some voltage sources and some current sources. Okay, so a good practice will be required, but after solving similar 3-4 problems, you will definitely get a clear idea of all the theorems and all the steps involved. Thank you very much.